All right, in the last video, we learned about first order reactions when we started talking about integrated rate laws. We're actually going to talk about zero order reactions next. They're a little weird. These ones are actually reactions that the rate is independent of concentration. That's a little unusual, but definitely not unheard of. Typically, these are things that are like light catalyzed. So basically, it doesn't really matter how much stuff you put in there. It has more to do with how much light is shining on it. Or surface catalyzed. Okay, so there are some things, I don't know why I hyphenated that. There are some things that it depends on how much surface contact between two things there are, and it depends less on the concentration and more on how much surface contact there is, but we can't measure that in terms of concentration, so it's technically considered zero order. So what that means for us is the rate is a constant. So, I mean, we could write it like this, but if you take any number and raise it to the zero, this disappears and it becomes equal to 1. So, rate is equal to K. That's what your rate law would look like. These are not unheard of, but they're not super common. In the last video, I spent a lot of time like showing you examples of the first order rate laws and all that stuff. This equation is actually pretty easy, and we're not going to do a whole lot with it, so it's not as common. So the first order ones come up all the time, though. Okay, but the integrated rate law for this looks like this. It's actually in the y equals mx plus b format, but it's basically concentration at time t equals negative kt plus the concentration of a sub 0. Okay, that's it. And there is a half-life equation for this as well. For this one, the half-life actually does depend on the concentration. So it's concentration at time 0 divided by 2 times K. So this is the integrated rate law. This is the half-life equation. Okay. And I know I arbitrarily kind of at the end of the last video, or towards the end of the last video, talked about plotting these things. You can do similar stuff with this. For this one, you'd be plotting concentration versus time, which seems like the most logical option. And because it's negative KT, you're gonna get a line, and it's negative K as your slope. So this is only true for zero order. So if you plot concentration versus time and it's a first order reaction, you're gonna get a weird curve. If you plot natural log of concentration versus time like we did in the last video of one of these, you're gonna get a weird curve. The only time they ever come out as straight lines is if you've got the right overall order of the reaction. And the beauty is, if you plot concentration versus time and you get a nice straight line, your rate law is really easy. It's just equal to whatever this thing is as a positive thing. Okay, so we've covered this one now. I'm not going to make a big deal of it. I'm not saying you'll never see it, but it's one of the less likely ones to come up. Okay, I want to jump straight into second order reactions. I can't write apparently. Order reactions. It is possible to have a second order reaction where you have rate equals K times one compound with a 1 and another compound with another 1, both of them are 1s. Those actually get really complicated. You actually have to visualize them as two separate first order reactions, and it gets really messy. We're going to deal explicitly with the ones where we have one reactant and its exponent happens to be a 2. This is what makes it second order. Okay, so literally when it comes to like choosing which equation to use, you literally just look at the exponents. Okay, so I'm just going to give you the equations here, and then we'll kind of work through an example and see how to use it. Okay, so the equation, the integrated rate law, looks like this. It is 1 over the concentration at time t equals positive KT plus 1 over concentration at time 0. So there's no natural logs, but we do have this inverse thing going on, which has its own complications. The half-life equation for this equals 1 over K, and A sub 0 is on the bottom. So each of these reactions has its own unique half-life equation. So you need to know whether it's 0 order, first order, second order, to know which set of equations to use. Okay. And for this one, if you were going to plot it, it would be 1 over concentration, because that would be your y-axis versus time. And for this one, you should get a positive slope because there's no negative sign in there. So you're going to get some sort of, basically, slope equal to k. And this is only true for second order. So we did an example of a first order calculation. Let's try one that's a second order. Okay. So kind of like we did with the first order one, we would have to have a rate log given to us. So let's say we've got rate equals 2.93 times 10 to the negative 4 inverse molar inverse seconds, which is the units that you work out for a second order reaction, times, let's say in this one, it's iodine squared. Okay, that 2 at the top tells you that it is second order. So the first part of this is if the initial concentration of I2 is 0.643 molar, we want to know what is the concentration at 200 seconds. Okay. Put a dot there to make it clear that that's 3 sig figs. Okay. Well, if you see this type of problem on a quiz or an exam, the first thing you want to do is double check your exponent. This is a 2. We are going to use these second order equations. Okay, if you try this with either of the other 2 options, you will not get an answer that makes any sense. Okay, so we're going to rewrite that equation so we have something to work with. We really don't need to rearrange much because it's kind of in terms of concentration of A sub t over here. Yes, it's inverted, but we'll deal with that right at the end. So K is 2.94 times 10 to the inverse, or 10 to the negative 4 inverse molar inverse seconds. T is 200 seconds, and this is 0.643. So I'm just going to plug everything in. So this is 2.94 times 10 to the negative 4th inverse molar inverse seconds times T, which is 200 seconds. The seconds will cancel out and we'll have 1 over molar as our unit, and that's fine. And then we add that to whatever 1 over 0.643 molar is. So this is 1 over molar, this is also 1 over molar, so we can add them together, which means that we've kind of set things up correctly. Okay, so in terms of plugging this in, we have 2.94, second EE negative 4 times 200. I'm just going to go ahead and hit equals, plus 1 divided by 0.643. And all of that together comes out to be 1.61 inverse molar. And this is equal to 1 over concentration. Well, that is not super useful. I mean, it kind of is, but we need concentration, not 1 over concentration. So we need this on the top, so we need to do the reciprocal of it, which means we need to do the reciprocal of both sides. So I'm going to put 1 over both of those. This will rewrite as, I'll just rewrite it down here, concentration at time t is equal to 1 over 1.61 inverse molar. And then we can plug that in and see what we get. Honestly, I'm just going to do 1 divided by second to answer because it's what I already had in there. And I got 0.6195, that would round up 0.620, I guess. Okay, well, we started at 0.643 and it went down to 0.620, which means we're nowhere near the half-life. 200, it's going to be way more than 200 seconds to get to the half-life. But part B is, what is the half-life? What is the half-life if the initial concentration is equal to 0.643? Okay, well, we have an equation for that. Saw it on the last page. This was the equation we just used. This is the half-life equation, and it's still a second order reaction, so we have to use this one now. So T1/2 is what we're solving for, and it's 1 over K is 2.93 times 10 to the negative fourth inverse molar inverse seconds. This is 0.643 molar. Okay, this is molar, well, ignoring, just in the denominator, this is molar on top, this is molar on bottom, they're going to cancel out. And we have 1 over seconds, so our units at the end should be seconds. Okay, I'm going to plug this all in and see what we get. 1 divided by 2.93 e to the negative 4 times 0.643, and I got 5,307, well, 308, but I guess we only need 3 sig figs, so 5,310 seconds. So we said that 200 seconds caused a very small change in our concentration. It makes sense that if we're going to get to half of that, it's going to take a lot more than 200 seconds. So I'm fine with you leaving it in seconds, but I'm now morbidly curious how many minutes that is. 88 minutes, so almost an hour and a half. Okay, so for some reactions that may be a very reasonable number. Okay, so at this point we have now seen first order, zero order, and second order reactions. I will tell you that there are third order, fourth order, but they almost never come up. Honestly, first and second order are the most likely options. So if you can do first and second order, and then also we did talk about zero order, so you are responsible for knowing how to do it, but it's the easy one of the bunch. As long as you know, so whenever you see a rate law given to you, the exponent at the top is going to tell you which reaction or which set of equations to use. If there's a 2, you're going to use these ones. If there's a 0, you're going to use these ones. If you're going to use 1, you're going to use the ones from the last video. Okay? But keeping this straight is critically important to getting the right answer here. Thank you.